Welcome back. In this lecture, we will cover flows at low Reynolds number. We live and practice engineering in a world that is essentially a high Reynolds number flow. Typical fast ball in cricket is at a Reynolds number about 2 into 10 to the power 5. A person swimming in water swims at about 4 into 10 to the power 6. The fastest fish is at about 10 to the power 8. A Boeing 747 airplane flies at 2 into 10 to the power 9. The RMS Queen Elizabeth II sailed at 5 into 10 to the power 9 Reynolds number. A tropical cyclone would have Reynolds number up to 10 to the power 12. Most engineered devices work in the range of Reynolds number about 10 to the power 3 to 10 to the power 9. However, there is a world out there with very small Reynolds numbers. This is the region where Reynolds number is less than 1. In this are included bacteria, planktons, ciliates, and other such small particles whose Reynolds number are less than 1. Transmission of COVID virus through aerosols from infected persons is a low Reynolds number phenomena. Air pollution, the 2.5 micrometer dust particles settle in air with a Reynolds number about 10 to the minus 4, while a 10 micrometer dust particle settles at a Reynolds number of 10 to the minus 2. In meteorology, the typical fog droplets of size 50 micrometers settle at a Reynolds number of 1.3. Slurry transport in chemical engineering is one phenomena where low Reynolds number prevail. Motility of sperms in infertility studies and action of cilia are also very low Reynolds number flows. A human sperm with a head of 550 micrometers travels at 200 micrometers per second in seminal plasma, which has a value of kinematic viscosity 10 times that of water. The Reynolds number is order 10 to the minus 2. Let's study the low Reynolds number flows in detail. We had non-dimensionalized the governing equations, the Navier-Stokes equation, and the non-dimensionalized governing equations in normalized variable looks like this. In this, the coefficient of the convective acceleration term has been made unity, and then the coefficient of the unsteady acceleration terms is 1 over Stowell number, of the pressure gradient is 1 over Euler number, of the gravity term is 1 over Froude number squared, and of the viscous flow 1 over Reynolds number. If Reynolds number is low, the viscous forces would have a coefficient which is much larger than 1. It is not convenient to us, so we multiply this equation across by Reynolds number to make the coefficient of the viscous term as 1. This is the resulting equation. Now, in this equation, the coefficient of the convective acceleration term is Reynolds number, and if the Reynolds number is very low compared to 1, this term can be neglected, at least in comparison with the viscous term. And if we neglect it, the resulting equation is this. Here, we have also done an additional manipulation where we combined the pressure term and the gravity terms by defining a non-gravitational pressure script P. And then the coefficient of the gradient of the script pressure P is Reynolds number by Euler number. You may note that this equation is linear in the velocity variable, which affords enormous simplification in its solution. The linearity of this equation, along with those of the applicable boundary conditions, permits superposition of elementary solutions to obtain more complex solutions. Stokes solved this equation in spherical polar coordinate for flow about a spherical body. Then he got the velocity components Vr, the radial velocity component, given by this equation, where capital R is the radius of the cylinder. The angle theta is measured from the horizontal axis, and R is the position vector. The theta component of velocity is this, and the pressure on the cylinder is given by this equation. We give these equations without proof because the mathematics involved is a little more complex for students at the first course level. If you plot the streamlines look like this. This shows the velocity profile at the shoulder of the sphere. This velocity V naught is the free stream velocity, the velocity with which the flow approaches the sphere. Notice that almost a diameter away from the sphere, the velocity is still quite small compared to V naught. We give here the flow about the same sphere in a high Reynolds number flow. In fact, in a infinite Reynolds number flow with no viscosity. Look at the velocity profile in this. It's quite different. Here, the velocity at the shoulder of the sphere is large, 3/2 V naught, compared to zero velocity in the Stokes law, and the velocity at a distance of about a diameter has already approached the velocity V naught. Remember, this flow solution is not a physical solution. This is for an idealized fluid with zero viscosity. No such fluid exists. This is only to illustrate the mathematical nature of the two equations. Let's study some distinguishing properties of the Stokes flow. The flow pattern is completely symmetrical. That is, the streamlines remain the same whether the flow approaches the sphere from left or from right. Even though the flow pattern is symmetrical, the pressure distribution is antisymmetrical. Thus, while the pressure is maximum at the nose, it is minimum at the tail, even though the velocity is the same at 2 points. This observation is in marked contrast to the behavior at large Reynolds number, where pressure at the nose and at the tail are exactly the same. The fluid velocity is significantly lower than the free stream value V naught over a considerable distance compared to the radius or the diameter of the sphere. In fact, you need to go as far out as R by capital R is equal to 16 before V approaches 99% of the V naught. This means that the effect of the presence of the sphere is felt over large distances. This is also unlike that in the case of high Reynolds number, where the flow velocity approaches the free stream velocity within less than 2 diameters from the center of the sphere. Because of the influence of the sphere over large distances in low Reynolds number flow, small particles moving at low Reynolds number interact strongly with one another. That is, the motion of a particle is affected by the presence of other particles, even when their separation is large compared to their diameter. This also is in sharp contrast with the motion of larger particles moving at higher Reynolds number, which have almost no such interactions. Another property, the pressure differences near the sphere are of order unity when scaled by mu V naught by d. Thus, the characteristic pressure difference delta P characteristic equals mu V naught by d. This was to be expected since the pressure force balance the viscous force, and hence the two terms in the equation must be of the same order. This also is in contrast with the high Reynolds number flow, where the characteristic difference is 1/2 rho V naught square, not dependent upon the viscosity at all. In the steady flow, the governing equations acquires the form minus Re divided by Eu. The Euler number delta star P star plus delta star square V star is equal to 0. Since delta star P star must be retained in the equation along with delta star square V star, Reynolds number by Euler number should be equal to 1 or of order 1, and that is why delta P characteristic is mu V naught by d. The total pressure and shear forces acting on the sphere in the horizontal directions are obtained as 2 pi mu RV naught and 4 pi mu RV naught respectively. These are obtained by integrating the horizontal component of the pressure forces and the shear forces over the entire surface of the sphere. Therefore, the total drag experienced by the sphere is the sum of the two. That is, the drag is equal to 6 pi mu RV naught, and the drag coefficient defined as CD is equal to drag divided by 1/2 rho V naught square A is 24 divided by Reynolds number based on the diameter. And A is the frontal area of the sphere, pi r square. Note that this definition of drag coefficient is not appropriate for low Reynolds number flow. But we do this in this manner because it is conventional in the high Reynolds number flow. And just to compare the drag coefficients, we have defined the drag coefficient in the low Reynolds number flow too in the same manner. When Reynolds number is very small, this drag coefficients become quite large. This drag 6 pi mu RV naught is what you learned in high school as Stokes law. It wasn't mentioned there that this is only at very low Reynolds number. It was given as the drag on a sphere. But now we know that this refers to drag on very small particles moving at very small velocities, like dust particles in air. Note that the drag in the Stokes formula does not depend upon the density of the fluid, confirming that the inertia of the fluid is unimportant for the Reynolds number flow. An interesting observation. Even though the governing equations for the low Reynolds number flow has been obtained by assuming the Reynolds number is low, these apply to many other situations where the convective acceleration is identically zero. As is always the case in fully developed flow, such as the Couette and the Poiseuille flows between two parallel plates and in flow through a pipe, whatever be the Reynolds number of the flow. There, the convective acceleration is identically equal to zero, and so it is only the pressure forces that balance the viscous forces. And so the equation is the same as the equation for the low Reynolds number flow, even though the Reynolds number could be very high in those flows. Motion due to impulsive start of an infinite plate, where again the convective accelerations are zero, and the Rayleigh-Stokes flow are other examples of flow where convective acceleration was exactly zero. Recall that these are the flows in which velocity does not change in the flow direction, so that the convective acceleration is identically equal to zero. For Couette-Poiseuille flow, we obtain this as the equation, and this could be written as this on non-dimensionalization, exactly the same equation that we are dealing with in low Reynolds number flow. Thus, Reynolds number, Euler number is of order 1 and delta P naught is of order mu V naught by D. The characteristic pressure difference in such flows are then related to viscous stresses and not to 1/2 rho v square. The characteristic pressure difference in flows where acceleration is significant. Now let's talk about quasi-steady flows. The governing equation in an unsteady flow at low Reynolds number was obtained like this. The unsteady term here has a coefficient equal to Reynolds number times the Stowell number, that is d square divided by nu t, where nu is the kinematic viscosity of the fluid, which is mu divided by rho, dynamic viscosity divided by the density. This term is negligibly small compared to the viscous term when tau is much greater than d square by nu. For the case of a human sperm with d is equal to 50 micrometer, swimming in the seminal plasma, which has a nu of 10 to the power minus 4 meter square per second, the value of d square by nu is 2.5 into 10 to the power minus 5 second. Thus, the unsteady inertial term is significant only for times as low as 25 microseconds and may be neglected after that. Also, if the boundary conditions change at a pace slower than the time scale of 25 microseconds, the flow may be considered as quasi-static. That is, we may treat the flow as steady at every instant to be solved with the conditions specified for that time. It is exactly the same picture as we did earlier when we have a flow above a plate which was oscillating. Then we saw that when the motion of the plate was slow, the time period was large, the velocity profile in the flow was like that for steady flow with the boundary condition varying with time. Thus, if a body travels through the fluid at an accelerating speed, we can obtain the drag on that body at any instant by considering a steady flow past the body at a speed equal to the speed of the body. Thus, while the inertia of the body is important in determining the motion of the body, the inertia of the fluid can be completely ignored if the flow is at very low Reynolds number. Let's do an example. Let's calculate the time to acquire the terminal velocity in low Reynolds number flows. When a ball falls in water or a helium balloon rises in the air, a steady velocity termed as a terminal velocity is attained when the drag force becomes equal to the net weight. That is the weight minus the buoyancy. For what order of time the accelerating motion can be neglected? Also determine the time after which the unsteady inertial term for the fluids are unimportant. For a steel sphere of diameter 0.1 millimeter settling in water, estimate these two characteristic times and explain the physical significance of these two times. Let's see what are the forces and let's estimate the forces. The inertial forces on the sphere would be like mass, which is like rho for the solid, the rho for steel, times d cube, which is like volume, multiplied by Vc by Tc, which would be the characteristic acceleration. The gravity forces on the sphere, which is the wet weight, is the density difference between the solid density and the liquid density to account for the buoyancy force, times g times the volume, which is like d cube. The viscous forces are like mu Vc into d. Inertial forces of fluid convection, we have done that a number of times earlier, is minus rho of fluid. It is like rho of fluids times the length squared times the velocity squared, and the unsteady inertial fluid forces would be like rho f d cube, which is like mass of the fluid times acceleration Vc by Tc. The ratio of the viscous forces to inertial forces of sphere are like rho s d square divided by mu Tc. Thus, the unsteady forces on the solid can be neglected if rho s d square divided by mu t is much less than 1 or t is greater than rho s d square by mu. We can neglect it if t is greater than this. So, for time less than this, we need to consider the unsteady forces. For a steel sphere of diameter 0.1 millimeter settling in water, this is 0.028 seconds, a very small time. Following the same logic, the unsteady or the inertial effects in fluids are negligible for time greater than rho f, the fluid density times d square by nu. This time for the same sphere is 0.011 second. less than half of the earlier time. So, for time less than 0.011 second, we cannot neglect the inertial effects within the fluid, but between 0.011 seconds and 0.028 seconds, we can neglect the inertial effects in the fluid, but not the acceleration of the steel sphere. But beyond 0.028 seconds, we could neglect the inertial effects completely, and the steel sphere would be traveling with terminal velocity. Let's do another example. The human sperm with a head of 50 micrometer diameter is traveling at 200 micrometers per second by moving its flagella in seminal plasma of kinematic viscosity about 10 to minus 4 meters square per second, as discussed before. It develops a Reynolds number of the order of 10 to minus 2. So it is a low Reynolds number flow indeed. Let's calculate the length over which the sperm will coast if it stops moving its flagella and just coasts. The deceleration it experiences is purely because of viscous forces, which have been estimated as mu d v naught. The mass of the sperm is estimated as rho times d cube, so that the deceleration is of order mu v naught divided by rho d square. And the coasting distance is then estimated as v naught square divided by deceleration, or L by d, which is like rho dv naught by mu, is like rho s divided by rho times Reynolds number. Rho solid divided by rho of fluid into Reynolds number. Since rho s by rho is like 1, the Reynolds number itself becomes the non-dimensional cruising distance. The value of Reynolds number here is 10 to minus 2. So the value of L by d, the cruising distance, coasting distance divided by the diameter of the sperm is 10 to minus 2, or the coasting distance is about 0.5 micrometer. This means that the sperm will stop moving almost immediately after it stops moving its flagella. We see from this that the response of a fluid at low Reynolds number to the motion of boundaries is practically instantaneous. Geoffrey Taylor of Oxford University conducted some experiments to show kinematic reversibility of low Reynolds number flows. The following film illustrates this effect.
Low Reynolds number flows are reversible when the direction of motion of the boundaries which gave rise to the flow is reversed. This may lead to some surprising situations which might almost make one believe that the fluid has a memory of its own. Here are two concentric cylinders. The fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea. Now I reverse the direction. and after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion.
In this picture, we saw that the rotation of the inner cylinder causes organized motion with the fluid layers sliding over one another. We have seen earlier that the motion in low Reynolds number flow is quasi-steady. This implies that time does not matter. The pattern of motion is the same whether slow or fast, forward or backward in time. Thus, the blob in the first figure becomes oblong in the second figure. It becomes part of a spiral in the third figure. And then we reverse the flow and we go through the stages, and finally we acquire the same blob shape, except for a little diffusion that might have taken place during this time. The distance traveled by each layer decreases in the direction of increasing radius, and therefore the blob acquires a spiral shape as shown. The dyed glycerin molecules spread out, but not randomly, the diffusion being too slow. On reversing the motion of the inner cylinder, the fluid layers slide back and reassemble as the blob. In low Reynolds number flow, we can extinguish a candle by suction if we could extinguish it by blowing. Is another matter that we cannot blow out such a candle. But if we could also suck it out because the motion is reversible. This cannot happen in the case of high Reynolds number flow, where it is easy to blow out a candle, but you can't suck it out. Kinematic reversibility is a direct consequence of the linearity of the governing equation in its steady form. The flow everywhere depends linearly on the instantaneous boundary conditions. If the velocity at the boundaries are reversed, the velocities are reversed everywhere, and so is the pressure. It's easy to demonstrate the kinematic reversibility by a deck of cards on the side of which we have painted this picture, and when we slide this deck, it acquires the shape. If we apply a force in the reverse direction to slide, we can get back the same. This very roughly gives you an idea of kinematic reversibility. Let us now talk of the falling bodies. We have talked of the terminal velocity, which is the velocity that a body acquires under the action of its own wet weight and the drag in the fluid it is moving. The Stokes equation gave the drag as 6 pi r mu v. For a sphere. But the interesting thing is that this drag does not depend upon the shape of the body. This graph here shows that at low Reynolds number less than 1, all points for 6 different types of bodies: sphere, ellipsoid shaped particles, cube shaped particles, and cylinder shaped particles, and frustum shaped particles have all the same drag coefficient. So it's quite independent of the shape of the body at very low Reynolds number. Of course, as the Reynolds number increases, this particle deviate from the line for the spherical particles. Since the weight of the particle varies like r cube and the drag on it varies like radius times the velocity, from the equation the drag is like 6 pi r mu v. The terminal velocity in this creeping flow limit varies like r square. The larger particle travels much faster than smaller particles. If the diameter of the particle is twice that of a smaller particle, then its terminal speed would be 4 times. This is seen in the fact that a terminal velocity of 2.5 micrometer dust particles, which cause a lot of air pollution, is about 1.5 into 10 to the minus 3 meters per second, 1.5 millimeter per second. While there are 10 micrometer particles, 4 times the diameter, the terminal speed is 2.4 centimeters per second compared to 1.5 millimeters per second. The effect of the presence of bead creeping down a fluid column is felt over a large distance. Because of this, the motion of beads far away from a moving bead are affected by its motion. The presence of nearby wall affects the motion of the beads. This happens only in low Reynolds number flow. It will not happen in high Reynolds number flow. Of the two beads, one close to a wall and the other far away, the bead close to the wall moves slower because of the presence of the wall. As a consequence of the kinematic reversibility, the bead travels at a constant distance from the wall. The effects referred to above have been demonstrated very well by Jeffrey Taylor in the same movie that we referred to above.
The drag of a falling sphere is proportional to its diameter and to its speed. The net weight of the sphere is proportional to the cube of its diameter. The velocity is therefore proportional to d squared. They have diameters in the ratio of 2 to 1, so that the larger one falls in syrup 4 times as fast as the smaller. At low Reynolds numbers, the disturbance produced by a moving ball extends many diameters, so that beads far from the ball are moved by its passing. Thus, the presence of a nearby wall can be important. Here are two identical balls, one near a wall and one far from it. The ball near the wall falls more slowly. Incidentally, it remains at a constant distance from the wall, a consequence of reversibility. This retarding effect also slows the fall of a particle surrounded by many similar ones, so that a cloud of them falls more slowly than a single one. When a cloud of assorted particles falls in a fluid, it develops a sharply defined top. A particle which has a terminal velocity rather lower than its neighbours doesn't always get left behind. If it did, it would find itself isolated and would fall faster and therefore catch up the rest.
Thank you very much.